session. I think if you have any question, you can take. Uh, okay, good. So I think we will start today. So today we will mostly confine ourselves on the Rietveld refinement. So previously we have done phase analysis. So what I will do, I'll just recap those things. Then we will go to the next topic. Okay. Okay. So before we start this ritual refinement, I will just go through that. So this is what we are going through the traditional approach. We are not going through the other one. So for traditional approach, what we do is we collect data on our sample. Then we will check the quality of the data. Quality of the data means you should have good intensity, good uh, good intensity. Then we should also have good noise, sorry, less noise, more better signal. Okay. And then also the resolution in the sense, if there are two peaks very close to each other, they should be easily differentiatable. Okay. If you cannot differentiate, if it is a monoclinic system, and if you are not able to differentiate two close by peaks, then what happens, it would be difficult to do the proper fitting. Okay. So then what you normally do is you can do two approach. The first approach is phase matching, what we did. So the phase matching will give more information about the symmetry and unit cell values. Okay. So this is from your reported data, okay, or from your reported or from the database. So you do this phase matching by using Quellex, Jade, Match, or so many. You can even use Topaz, EVA, and I think High Score Plus. Okay, so you can use any of those things. The main information that you get from phase matching is the symmetry. Symmetry in the sense what space group it is, what kind of symmetry it is having, whether it is a cubic, tetragonal, orthorhombic, and then you will also get some unit cell parameter. Okay, so this you get it by matching with your database. Okay, the second thing what we did was we also did the profile fitting, or in to be more precise, we did Libé fitting. So Libé fitting would give more precise this unit cell and symmetry for your sample. Okay, the one what you get in this case, in case of your reported, is from it is a rough estimate. It's not the unit cell parameter is not for your sample. Okay, so it is just the starting values. But when you do a Libé fitting or a profile fitting, you get unit cell parameter for your sample. Okay, so there may be some shift in the ABC parameters due to some experimental condition, or you may be doing some intentional doping. So when you do some doping, there may be some shift in the ABC parameters. Those things you get from the Libé fitting or your profile fitting. You can also do poly fitting, but in full proof, normally we do the Libé fitting. Okay, so if you're using some other software, you may also have option to do poly fitting or something like that. Okay, so let us, but for your first preliminary information, your Libé fitting is sufficient. Okay, because you want to know the unit cell parameter, and also we will try to do the know the proper symmetry. Okay, that means what is the proper space group for your sample. And along with that, this will also consider the this will also give more information about the instrument parameter. Okay, instrument means like your UVW parameter or XY parameter. So if I am using Thomson Cox, so Thomson Cox testing, then we are going to refine mostly your XY and W. Okay, in some cases W, if not, it's not necessary. Okay, so and also your background. So background depends on your instrument and also the way you collect the data. Okay, so those things are taken care by your profile fitting. So again, I think I just put some so I'm just showing this because we started from here. So you can take your lab X-ray or synchrotron or neutron data, So this data collection, from data collection, what we did is we reached this libafitting. So this is where we are right now. So next, what we are supposed to do is we have to give the more information about your sample, like your chemical information, and then you can choose a model, or you can also do a reciprocal lattice. But we won't go more on this reciprocal lattice. We will choose a model, and then you can also you can also know whether it is a single phase or multi phase. Okay, so those things we have already done by using your lab fitting. Okay, so now what we will do is we will try to go for the next one, which is your structural or complete refinement. Okay, so before that I will just again give very brief summary of what we did in the previous one. Okay, so first thing what we did was we did the phase matching. So in phase matching, what we did, we learned all those things. So that in case of phase matching, we should take care of the position of the peak and also the intensity of the peak. Okay. So only then, if you can match both position and intensity, then you can get a phase match, or you can get the preliminary information. Okay. So then we also saw something about solid solutions. So solid solution, for example, if you have cerium oxide, then if you dope something, and then there will be a shift in the in your peaks. Okay. So in the previous case, this is not a solid solution. This is just a mixture, okay, or composite. So where you have two phase separately existing. Okay. In the next thing, in solid solution, what happens is you'll have a single phase, but you'll have shift due to the introduction of some new element into your lattice or your crystal structure. Okay. So then you also knew what are the you had three forms of your crystallinity. So one is your single crystal, polycrystal, and then amorphous. Okay. So when you take amorphous, there is no proper arrangement, or there is no regular arrangement of atoms. So in this case, what happens? You cannot satisfy your Bragg's law, because when you want to satisfy Bragg's law, there should be at least two layers of repeated arrangement. Okay. So for example, if you take a polycrystalline, so you can see the polycrystalline is just like small crystals. So if you see, there is some different uh, grains here. So if I consider this is a first grain, this is second grain, this is next grain, then what happens? If I take this top grain, you can see these atoms are in having regular arrangement. Okay, maybe like four rows are in same repeated arrangement. If I take the next one, so then what happens? There is a tilt in this arrangement, but still I can have at least three rows of repeated arrangement of atoms. Okay, so but when it comes to single crystal, the entire crystal will having the same arrangement. So it is like just repeating the same rows in or repeating the arrangement of atoms in several rows and several columns. Okay, so then this becomes a single crystal. So when you take a single crystal, you have more ordered arrangement of atoms. So you get very good intensity, because you will have same similar uh, what or you will get a very good repeated arrangement. So the intensity is better. Okay, but in case of polycrystalline, what happens? There is some arrangement, but it is not it is not spread over the entire sample. Instead, it is localized. Okay, so still in this case, you can get good intensity of your for your peaks. Okay, but in case of amorphous, what happens is you don't have any arrangement, so it is very difficult to have consecutive interference in this case. Okay, so normally what you get, if you take amorphous like your glass, if you just make a X-ray, uh, if you try to make X-ray diffraction on this amorphous sample, what you get is you just get some hump. Okay, so this is just mainly because it is like a scattering, not diffraction, but it's more like a scattering. Okay, so your each atom will start giving some scattering, and then it will give a hump. Okay, so but when you take, if you want to take crystalline sample, then it may be a polycrystalline or a single crystal. So in that case, what happens? You get well-defined peaks at different 2 theta position. So now, if I have a mixture, like if I take these 3 things, so similar to what we did in the first case, okay. So in this case, we took SiO2 and NaCl. So along with that, if I have a third phase, which is a amorphous phase, so then if I mix everything and then if I do X-ray diffraction, what I get is the addition of all the things, okay. So you can see there is a hump. This hump is due to some amorphous form which is present in your sample. And there are peaks. So this peaks is, you can say now that this is from your cristobalite, so your second phase, and then the small peak is a small peak, and the next peak is due to your quartz. Okay, so just a minute. Okay, so this is fine. Okay, so this is how you can also get if I do a quantification, I can do quantification of even for a non-crystalline or amorphous phase. Okay, so this is mostly used in case of pharmaceutical companies. So where they even want to know the amorphous form. Okay, so now if you take this mixture, then you can also try to deconvolute contribution of your amorphous and also crystalline form. Okay. Okay. So now when it comes to, so there are some things that you need to take care. So if you want to say if it is having a good match means if you are having a very good phase identification, then you need to take care of these things. One is, you can see here, this is at very high angle. So you are having position and intensity is matching. Okay, so this is having slightly around 400 intensity. This may be having something like 250 intensity. Okay, but this is also matching with your trend in your sample. Okay, so same thing in case of your this 3 peaks. So in this case, what is happening is you also have something as K alpha 2. Okay, so the second peak is mostly from K alpha 2. Same thing in this case. Okay, so for the peak which is in the middle, the K alpha 2 is almost coinciding with the peak position of your third peak. Okay, so in that case you may not see the K alpha 2. Instead, you will have some intensity difference. Okay, in this case, then you can if you go to even slightly higher angles, so you will have something like this. Okay, so for example, here the peaks are very close, and then if you see take the intensity is matching, but in some cases what happens, the intensity is matching for big peaks, but some small peaks, there may be some small what is it, difference in the intensity. Sometimes you can still take this because if you see most of the other peaks, it is matching. Okay, the peak position and the intensity is matching. Only some peaks are not matching. Okay, so this can be due to some other reasoning. So that we will see again. Okay, so but you cannot consider a match when you miss some peaks. Okay, for example, in this case, this peak is having more intensity compared to the next one. Okay, so this, but if you are able to see this small peaks, but you are not able to see the bigger peaks. Okay, so in this case, what happens, this is not a proper match. I cannot consider this is my match. Okay, even if you see here, what happens is this small peak is not appearing actually. Okay, so as this peak is appearing, so this intensity is the intensity of this peak is more than the intensity of this peak. Okay, so in that case, if you are not able to see this peak, that means I cannot say this is a good match. Okay, or this is not a good what is that starting point. Okay, but you may not see the small peaks. This is acceptable, but when it comes to major peaks, you should see most of the major peaks. Okay, if you don't see those major peaks, then that means this is not a good match. Okay, or this is not a good starting model for your sample. Okay, so and then we also saw some mixed phases. For example, this is 3 phases. So you can see the blue lines are coming from hematite, which is your iron oxide, and then your green one is coming from diiodonatase phase, and then there is a rutile phase which is actually shown in your red. Okay, and if you consider the peak intensity and peak position, so intensity ratio for your red is almost having the same trend as your reported one. Okay, so then when it comes to even for your hematite, you can see the peak position and intensity ratio is almost matching. Okay, so this is how this is a good this is one of the example for good phase identification. Okay, so from this match, what you get is starting model for your space group and your ABC parameter. Okay, okay. So then we did this all these things. So I will just skip this. Then what I will do is I will go for the main topic for today's session, which is your ritual refinement. Okay. So I think I have some. If there is some question, I will check it. Okay. Why code change from 0 to 1 in PCR find during the profile matching? Is it necessary for all materials? Yes, this is if you have to change your code for 0 to 1. That means, as I told, 0 is used to do the instrument correction. Okay, there may be some shift in the peaks due to some instrumentation. That is maybe because of your sample height, or maybe due to your some change in the your X-ray and your detector position. Okay, so this 0 will take care of all these instrument changes. So that is the reason you need to do this 0 shift. Okay, but when it comes to retool refinement, we are going to change, stop it. Okay, so right now when you do a profile matching, you need to change this, or you have to run this 1 for your 0. Okay, so this is necessary for all the materials when you are doing a profile match. Okay, not when you do the retool refinement. So that I will explain again. Okay, so next one is for unknown sample. So for unknown sample, how we know this one is a major peak or not? So for unknown sample, we will discuss this again in a separate session where we are going to do a indexing. Okay, so I will try to cover that today or maybe tomorrow. Okay, so the indexing. So this I will again explain it. So it's let us not worry now. Okay. So when it comes to, so let us come back to this ritual refinement. So we have done profile fitting using your Libre fitting. So in this case, what happens is we have done. Sorry, just a minute. Okay, so now in case of your profile fitting, we have just taken care of only the instrument parameter, your UVW parameter, and then we have taken care of the your ABC parameter and space group. But when it comes to a complete refinement, then you need to take into account your atoms which are present in your sample. Okay, so that is what we are going to do in case of your ritual refinement. Okay, so I will just again come here. So we have covered the up to here. Okay, so we have covered all these steps. So now what we'll do is we are going to take care of this next step, which is your ritual refinement, where we are going to introduce the atomic positions, position of your atom, and then occupancy of your atom, anisotropy, thermal displacement, all these things. Okay, so only then it becomes a complete refinement. Okay, so up to here it is not a refinement, it's not called a ritual refinement, it is just Libre fitting. Okay, so or profile fitting. So now let us see what are things that is necessary for your ritual refinement. Okay, so for even if you want to do a profile fit, you can do it even on a regular data. Okay, even if you take just 15 minutes 20 minutes scan, you can still do profile matching on that. Okay, or profile fitting on that. This will give very rough idea. Okay, whether you are having a pure phase or not. For example, uh, if you're trying to form a barium titanate. Okay, so what normally you do is you take barium carbonate, you take some titanium oxide, or you may start from this is like your solid state reaction. Okay, so if you take these two samples and or two compounds, then what you do, you just mix it with a water vessel, and then you try to heat it at a high temperature. Okay, you will try to do heat treatment at different temperatures, so maybe at 800, 900, 1000, 1200. So normally if you're doing barium titanate, it normally forms at 1200, but normally you don't directly heat it at 1200. Instead what you do is you heat it at 800, 900. This is mainly to do some uh, decarbonation. Okay, so because you have barium carbonate, it has a lot of carbon, so you want to remove that carbon because you are trying to form a BATI O2 O3. Okay, so in that case what happens is so I will try to write here. Okay, so maybe so you are taking a barium carbonate BaCaO3. Okay, then you also take some titanium oxide TiO2, and you want your main product is you want some barium titanate BaTiO3. Okay, and then there will be some products like carbon dioxide and all those things. Okay, so we don't worry about the byproduct because this will be escaped into your atmosphere by at high temperature. Okay, so first thing what you do is you try to have a, sorry, this is O2. Okay, sorry. So you need to get rid of all these you need to get rid of all this carbonate. Okay, carbon dioxide and all those things. So for that you heat it 900 or something like that. Okay, so when you heat it at 900, there will be some uh, very small reaction between your barium carbonate and titanium oxide. It won't be complete. Okay, so in that case what happens, you may have some multi phases like some form of barium titanate, some of your barium carbonate, and some of your TiO2. Okay, so you just you want to check whether it has formed or not. So what you normally do is you take a very quick scan, like your 20 minutes or 30-minute scan. Okay, and then you can do this profile matching. Okay, and then you can see whether it has really formed the barium titanate, or it is having some along with that, is there any TiO2 and all this. Okay, so once you start heating at different temperature, higher temperature, and for longer time, maybe at 1200 degrees C for maybe 24 hours. So then after that, what if you take your XRD, then what happens, you will not see any of these bicarbonate byproducts. Okay, you will see only pure barium titanate. So once you have this pure barium titanate, what you are supposed to do is you need to take a very good data for doing your Rietveld refinement. Okay, so you cannot just do Rietveld refinement on a very on data which is having high background or high or some impurities. Okay, then it is not a good refinement because you will have a secondary phase or your data is not good. Okay, so we'll see why you need a good data. So what is the meaning of good data? Good data means a good powder sample is a regular assembly of very large number of tiny single crystal, because it's a polycrystal. Okay, that are oriented in random direction. Okay, and also you should try to have very narrow distribution of sizes. So, okay, the reason is the size broadening would also depend on the your crystallite size. Sometimes what happens, some people you just heat it at 1200 and then you just take this sample to X-ray diffraction. That is not really good for if you want to do a qualitative analysis or quantitative analysis. So if you want to do really good qualitative analysis, then try to grind it and have a narrow size of your crystals. Okay, so normally if you want to do this, what you can do is you can do this sieving process. So you can take sieve of known size. Okay, so you can have a sieve of 50 micrometer. Then what you do is you grind the sample, you put your sample on this sieve. So sieve means is normally having some regular arrangement of these holes. Okay, and the hole size would be fixed, maybe like 50 or 100 or whatever is the size of this sieve. Okay, and then you once you put on this, then you just shake it. What happens is you get powder which is only of this particular size, okay, or maybe less than this size. So in that case, what happens? You are already having a very narrow size crystals. Then you'll have less contribution from anisotropy. Anisotropy in the sense your size anisotropy. It can be even from size. Okay, so you may have some particles which is 100 micrometer, which some may be 200 micrometer, some may be 50 micrometer. Okay, so you want to get rid of that. How to get rid of that? This is one of the method to get rid of that. Okay, then what you do is you have to also take care of so you have to prepare your sample. So this is one of the samples which we used to do in ICMCB in Bordeaux. So this, some of the slides are also from Stan, who is in charge of this XRD, and then he is giving some uh, training regularly. Okay, so every year, 2 years he is giving training. So I just took some of the slides. So normally this is it can be, your sample can be different color. Like if you are using titanium oxide, it may be white. You may be having some other oxides which may be black. Okay, so copper oxide, for example, is simple in simple terms. You can also have like praseodymium, strontium, manganese oxide, all those things. They will be in different color. So this is one more sample which is with its, some yellow color. Okay. So in this case, as you can see, there is a depth here. Depth in the sense there is a there is some hole here in this sample holder with some maybe 1 mm depth. So normally when you prepare the sample, you can see it should be only within that cavity. Okay, if you're putting out of this, then what happens? There may be shift in your peaks. So always try to cover this cavity with your sample. And how you do that? You can just use a blade, you put your sample, and then what you do, you use a blade to just fill this cavity. And the extra sample would be somewhere on this surface. Okay, so you can just get rid of that. You just scrape it off, like you just remove the sample, excess sample, which is on this platform. Okay, and then you can use a tissue to just get rid of all the extra sample which is on this sample holder. Okay, so in this case what happens, you have very nice packing of the your powder, and as you're done size uh, size selection, so you will not have any anisotropy due to your size. Okay, so you will have really good data, and then you can do qualitative analysis. Okay, and there are some other things which you need to take care. So especially your background. So you may not get really flat background all the time. Okay, so you may not get like this. Instead you may be having some lot of noise or something. So how to get rid of this noise? First thing is, you collect for a long time. Then what happens? Your signal to noise ratio is good. Then you get better signal compared to less compared to the noise. Okay, or your background. So that is one thing. And then this background can be due to your scattering from the slits. Okay, so as I told, you are using a slit. So when your X-ray is passing through the slits, this X-ray may also get scattered due to the edges of these slits. So normally these slits are made of lead. So in that case, what happens? You have less scattering. Okay, but if not, there may be some scattering. So, and also there may be some scattering from the sample holder. If you don't have a very narrow slit, then your X-ray may fall on this sample holder. Then you can have scattering due to the sample holder also. Okay, so those things you need to take care. And then thermal diffusion scattering, so this will come again. So, and there are some other things like fluorescence. For example, fluorescence, if you are using iron sample or some cobalt sample, and if you are trying to use your copper radiation, copper K alpha 1 and alpha 2, then what happens? There is a lot of fluorescence from this iron, and one way to reduce that is you can put a mask after the diffraction. Okay, so you have your sample. So normally most of the people, they put the mask before the sample. So you can ask uh, X-ray person or your X-ray in charge to put the sample after your diffraction. Okay, so after your sample. So in that case, you can reduce this kind of fluorescence. So normally, if you have fluorescence, then what happens? This background is going up instead of going straight. Okay, and it will also have a lot of scattering. So This we saw in case of when I was explaining the diffraction. Okay, so this is one of the way to reduce this fluorescence. The second way is if you have some other X-rays, like you, instead of copper, if you have cobalt or if you have molybdenum, you can use those kind of X-ray source, and then you can actually you can reduce the fluorescence. Okay, so these are some of the things that you need to take care when you want to collect a good data. So next, so the experimental condition should be optimized. So this is what I mean. So you need to optimize your experimental condition to get good intensity. Okay, so that is to reduce your background. So that is your main aim for in this case. Okay. So next, when it comes to your peak width, so peak width is as we had already discussed in the previous session. This peak width can be due to your sample and also due to your instrument. Okay, so those things you need to take care. So anyhow we will not discuss again because we already discussed those things. So this can be due to your the peak width can be due to your instrumentation or even just due to sample. Sometimes if you have strain in the sample, then again the peak will become broader. Okay, so those things we have already discussed, so we will not worry too much, because I have already explained this can be taken care by choosing a very proper peak shape function, like whether you are using Gaussian, Lorentzian, pseudo-wide or Thomson-Cox testing. So if you use these things, you can take care of the peak width. Okay, so now much important thing is is your intensity of your peak. Okay, so I don't want to scare you right now. Just just a minute. Okay, you can share, so you don't you can share the links because please feel to share the links. Okay, we don't mind if there are more people. Okay, if your friends are there, if they want to join online session, even if they are not registered, there's not a it's not a problem. Okay, so you can please share the links with your friends and your colleagues. Okay, so don't hesitate, you can share it. Okay, so I don't want to scare you by putting such a big equation. Okay, so it's not. But I just want to tell you because you should know what are the parameters that are giving the intensity. Okay, so similar to your peak width. Okay, so when it comes to peak width, you have contribution from your instrument. Like if you use a big slit, then your peak is broader. If I narrow down the slits, then what happens? It may be your solar slits which are in horizontal way, and it can be your divergent slits which are in perpendicular. Okay, so if I use this narrower slits, then what happens? Peak will become sharper. So that is about the peak width. Okay, so when we talk about the peak width, these are the things. And also if you have strain, then what happens? Your peak will become broader. If there is less strain, then the peak will be narrower. Okay, so these are some of the reasons for the peak width. In the same way, when you want to know the intensity, what are the contributions for the intensity? So these are the things which are contributing for your intensity. Okay, the first one is your geometry. Geometry means your X-ray diffractometer geometry. So you can see here r is the radius of your geometry. Okay, so as we told, your sample is in the center. Okay, and then there is a X-ray tube. So if this is your tube, and then there is a detector which is at equal distance in the opposite. Okay, so this is your detector. Okay, it can be your solid state detector, or it can be your even your gas detector. Okay, so this is going to move in a circle, right? So this radius, whatever you take, is your r. Okay, so this intensity depends on this r. Okay, so if you are close by, then what happens? Your intensity is better. If you go far away, uh, then it will so pressure as well. Okay. So if you go far away, then if you keep this tube and detector far away, then what happens? Your intensity will be less. Okay. So this is your geometry. So this come from your geometry. Then what happens? Next one is your scattering, electron scattering. Okay. So as we know, this X-ray diffraction is electromagnetic diffraction. It is mostly like a electromagnetic diffraction. So this again depends on the on this scattering also. Okay. So there is a contribution from electron scattering. So if you have more electrons, you have better scattering, and then if you have less electrons, then there is less scattering. Okay. So this is again depends on the second factor is your electron scattering, and then I will come to these two in detail. So then you also have something called as X-ray polarization. So as we are having a lot of optics which we are using in our diffraction, because we have a lot of slits, we have a mask, we are using mask to get rid of the fluorescence, all those things. So this there will be some polarization effect in your during the data collection. Okay. So this will also contribute for your intensity, and the last one is your absorbance. Okay. So as we know, like each element has different size. In the same way, each element, each atom, like if I'm using cerium, then it has a different X-ray absorption. If I take lead, it has a different X-ray absorbance, and if I take titanium, then what happens? It has a different absorbance. Okay. So this is the meaning of absorbance. Okay. Depending on the element which are present in your sample, it will have different absorbance, and this is taken care by this equation. Okay. So in this case, you don't have to worry about all these things. So your geometry, your scattering, your polarization, and also absorbance, this is taken care by your foolproof program. Okay. The program is written such a way that all these things are taken care by your program. Okay. You don't have to worry much about these things. Okay. But you need to take care of two things. First one is your symmetry, and then the second one is your structural factor. Okay. I will explain in the next case what is the symmetry. Okay. So you need to take care of these things, then rest will be taken care by your program. Okay. So this equation, whatever is there in the next part, is just your so this is very simple form of your the big equation. Okay. So you can see here K is the wavelength proportionality factor, Lorentzian, all these things. Okay. So these two things, these two equation are same, but this is very simplified version. The one which is in the green, marked in green, compared to the one in the first one. Okay. So compared to this is a simple one, but you don't worry too much. It is very simple. Okay. So now when it comes to symmetry and your form factor. Okay. Sorry. So now we will talk first about the structure factor. Then I will explain the symmetry. Okay. When it comes to structure factor, you have here this is F of HKL is your structural factor. What are the things that is there? Again, this is a one more equation, summation equation. Okay. So this is a summation of N, Fi, Fj, E, and all these things. So it is given here. What is this Nj? Nj refers to the number of atoms. Okay, J type of atoms. For example, if I take CO2, how many number of cerium is there in this in your sample? That is your Nj. Okay, number of cerium is there. So if you take CO2 for example, then what happens? So if I take CO2, for instance, so then what happens? So how many number of cerium oxide atom is there, and then how many number of oxygen atom is there? That will contribute for N. Okay. So N is taken care by this one, and then when it comes to your Fj is the atomic scattering factor of that particular atom. Okay, that means, as I told, there is absorbance. In the same way, how much your cerium can reflect or diffract, how much your oxygen can diffract. So that is taken care by Fj, which is your atomic scattering. So atom means cerium scattering, oxygen scattering. So I'm just talking only about cerium oxide because this is very simple. In the same way, you can have TiO2, you can have BaTiO3, you can have so many other things. Okay, even you can have intermetallic like gadolinium GdCOSi. Okay, in that case, what happens? This would depend on the element which is present in your sample. Okay, then what is Bj? Bj is the thermal displacement factor of your atom. Okay, so what is the displacement of cerium, thermal displacement, and what is the thermal displacement of oxygen? Okay, then there is something called as XYZ. XYZ actually corresponds to the coordinates. So if you take a lattice unit cell, okay, for example, if you take a unit cell, so if this is your unit cell, then what happens? So let's take this is a unit cell, and if I take very simple example, like if it is a simple cubic, then what happens? Atoms are in the corners. Okay, so now you may have NaCl. So for example, this is Na, then this is Cl, and then again you have Na in this case. Okay, and then the neighboring would be Cl. Okay, so this XYZ would give the position of your Na or Cl. Okay, so for example, if I want to say Na is at 111, then what happens? XYZ Z would become 111. So these are the coordinates of your atomic position. Okay, this again I will explain in the next slide. Okay, so now here what you are supposed to do is this structure factor is it contains all this information. Okay, it contains what is the type of atom which is present in your it depends on what is the type of atom. Okay, for example, if I take TiO2 and then cerium CO2, uh, titanium would have a different atomic scattering compared to cerium oxide. That is why you will get a different pattern when you're doing TiO2 or CO2. Okay, yeah, and even if it is having the same symmetry, for example, then still this intensity of CO2 would be different for intensity of TiO2. Okay, so if we assume both are having the same symmetry, but we are symmetry itself is a big or it itself is a different, it itself will give a big difference in your intensity. Okay, so you need to know these things. Okay, so if I now replace cerium with some zirconium, then what happens? The scattering of zirconium is not same as the cerium oxide, so you'll have different scattering factor. So the intensity may change. Okay, and then there is one more thing which is thermal displacement. Okay, what is this thermal displacement? For example, if I take even CO2, cerium is a heavy element compared to oxygen, right? Cerium would be having it will sit in or it is going to be in a stable state compared to oxygen, right? So if I start heating this sample, that means if I give some thermal energy for this sample, then what happens? The oxygen atoms would move faster compared to cerium oxide. Cerium, okay. Even cerium would be in some kind of small displacement. Even at room temperature, if you take room temperature, it is already 300 Kelvin, right? So even at 300 Kelvin means if you take P is equal to RT, real relation, this itself is already having some thermal energy. So even if you take cerium oxide data at room temperature, there will be some kind of thermal displacement of cerium and oxygen, right? Because it is already having some energy. So this is the main reason why they perform low temperature diffractions, like it may be X-ray diffraction, neutron diffraction. So one of the main reason why they do this low temperature measurement is when you go for low temperature, that means you are minimizing the thermal displacement, right? So you are having less thermal energy. So these atoms would be in their own position. Okay, that means the vibration even at this position, the atom may be slightly vibrating. In that case, what happens? Your diffraction is slightly distorted, right? So if you go to low temperature, then what happens? These atoms are very much fixed in their position. So there is less thermal displacement. Okay. So when you do this refinement, you need to take care of all these things. What is the type of atom which is present? Whether then how many number of atoms are present? For example, if I dope this cerium with some zirconia, then what happens? Ce, it is not CO2. Instead, it will be C.1. Then C.9, then zirconia 0.1, and then O2. Okay, so all these things should be, we need to give all this information into this into into the program. Okay, so we will see how to do that later. Okay, so cerium would be 0.9, zirconium will be 0.1 in that case. So if you are taking pure cerium, then what happens? Cerium will be 1, then O2, O will be 2. So these things is the number of atoms which are present in your sample. And then atomic scattering is again taken care by your program. Don't worry about that. But B ISO, you can do the modeling, and also XYZ parameter. That means what is the position of your atom that you need to give in your program, okay, or your modeling. So now, when it comes to symmetry, we can talk about the symmetry for 1.5 hours. So I don't want to spend too much time on the symmetry, but you need to know that when you are changing the symmetry, you're changing the factor here. This factor would be changing, so the intensity is going to change during that time. Okay. Okay, so that is why symmetry will also contribute for the intensity. Okay, so now when it comes to symmetry, so you need to know about symmetry. There are 7 crystal classes. So this we already discussed in the previous one. So you have cubic, then tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, all those things. So you have 7 systems. Someone is, so you please, all of you please mute it, because if not it will disturb. Okay. So when it comes to symmetry, it is mainly due to the arrangement of your atoms. Okay. So this comes from your unit cell. If you want to say unit cell, then you need to know what is the crystal structure of that unit cell. So there are 7 crystal classes, which is your cubic, then you have your tetragonal, orthorhombic, all those things. And then you combine those systems, 7 systems, with the lava class and crystal class and lattice centering. Lattice centering is mainly the symmetry operation that you can have. Okay, so in case of in some cases you can have mirror symmetry, you can have inverse symmetry, you can have all those things. So considering all those things, what you can have is, you can have 230 space groups. Okay, so this is just the different space groups that are given here. Okay, starting from your cubic, which is Fm minus 3m. So Fm minus 3m, if I say Fm minus 3m, then what happens? It is a face centered, uh, F is refers to face centered, and then let me check. Okay, I think it's not there. Okay, so if you take, I'll just, maybe I'll go here. Okay, so if you even give your space group, so, or even if you Google and if you go to Wikipedia, you will get all those 230 space groups. Okay, I think I will share this, some of these PowerPoints. So I will just do space group. Okay, search on my Google, then I will try to go for this one, or yeah, it's fine. Just okay. So I think I will go to this list of space groups on Wikipedia. Okay. So if you go to this, then you can see all these lists which are there. Okay. So if I go to, I will go to the simple one, which is your cubic. So if you go to cubic, I think the last one, from 195 number. Okay, so these are the numbers which are given based on the your symmetry. Okay, so if you take this 195, then the space group is, there's a number for that. So 195 with P23. Okay, or we will go very simple one, because let us not make you more confused. For example, Fm minus 3m. Okay, so Fm minus 3m means it is a face centered cubic. If I take Pm minus 3m, then Pm then it is primitive. Primitive means it is simple cubic, where you have atom only in the corners. For face centered, what happens? You have atom in the corner, and along with that you have atom in each corner. Okay, and then depending on the symmetry that you can have more mirror symmetry, then you can have inversion, all these things. Then you can give this kind of numbers. Okay, and then if you can also have body centered. So when it comes to body centered, IEM minus 3m. I means it is a body center. Okay, F means it is face centered, P means it is primitive, or it is very simple cubic. Okay, so then apart from that, you can also have different symmetries, like instead of Fm minus 3m, you can also have Fm minus 3c. So this is again, if you want to learn this, then you better go, and I would suggest you to I will suggest and I will send you this thing. Okay, so this is a very nice talks. So you can go through these talks, and you can know what are these things. Okay, so we will not go into this, because you can see here. So what are the you can also have two-fold, three-fold, four-fold, six-fold symmetry operations. So all these things would come to contribute into your space group. Okay, when I say Fm minus 3m, m is the mirror symmetry, then minus 3 is the three-fold symmetry, all those things. So we will not go into detail that, because that itself we can talk about for maybe 3 hours. So all these things would be important. So if you change the symmetry, then the intensity would change. So in your case, you should take care of this symmetry, and you should also take care of the structure factor. Okay, that means what kind of element is present, and what is the atomic position of that. All those things you need to take care. Okay, in the same way, you need to take care of the proper space group. I should not put Fm3m. Fm3m is different compared to Fm minus 3m. So in the same way, I cannot put some P4 by mm instead of Fm minus 3m. P4 by mm is tetragonal compared to your Fm minus 3m, which is a cubic. Okay, so those things I need to take care, and I should take care of the all these type of atoms and position of atoms, and your thermal displacement, all those. Okay, so from with this, what we'll do is we'll go to next one. So how to get all this information? So if you want to know the symmetry, for example, we can just do profile matching. That is why we did in the first case we did profile matching by using Quellex. Okay, from there you get information about your space group. You'll also get information about the your ABC parameters. Okay, so then what is the next thing? Next thing is your atomic position. Okay? So how to get the atomic position? Atomic position you can get from this kind of databases, but most of the things what happens is, if you take this ICDD database, which is your International Crystal Diffraction data, this is not a free version. You have to pay. Okay, so there is something called as PDF2, PDF4. Okay, so if you are working on some inorganic thing, you can use PDF2 and PDF4. But if you are using organic, then you need to go for higher or very new version of PDF. Okay, so these things you can get it from these websites, but most of them are you need to pay it. Okay, but there is one which is your open database. Okay, so this is a free database. This is the one which we are actually importing in our Quellex. Okay, COD is your crystallographic open database, and this is a free open access, and rest you need to pay. You can also use some softwares like Match, your EVA, or your Export High Score. Okay, so these softwares will also give the your or your crystallographic information file. Okay, so you can download this zip file, and then you can just use it in your full perf. Okay, so there is other free version. So all these things are mostly free version. So the first one is crystallography.net. Second one is mineralsproject.org. Okay, and there is one which is called as Bilbao crystallographic server. So this is a Spanish Spanish open source, and you can also use these things. So I will show you how to get this information. Okay, so normally you can download it from this website, or even nowadays when you go and when you see some publication, they already give some zip file uh, uh, with their publication. Okay, so when you download your publication, they give some supporting information. In supporting information, some people they already give this zip file. So you can also use that zip file as a starting model. So to have a starting model, you can use those kind of zip files, and you can start doing the your refinement. So if it is completely new structure, like you have tried to synthesize some new compound, and it is giving a completely new structure which is not reported in your any of these database, then what you do is you have to go for indexing. That I will try to cover in tomorrow. Okay, so that is completely different approach. Okay, so but in principle you can always try to get a zip file for most of your compounds. Like if you take your barium titanate, even your intermetallics, so there is already reported values in literature. Okay, you can take from you can take that as the starting model, then you can do a refinement, and you can try to do fitting. Okay, so now what we did in the previous case is what we call as a whole pattern profile fitting. So profile fitting is whole pattern profile fitting. So in our case we did leeway fitting. Okay, so this slide again I took it from my old lab. So normally there what you do is you normally play with the ABC alpha beta gamma and also UVW XY parameters. Okay, so as and if even if some if there is any asymmetry, you can do fitting. So this is just taking care of your lattice parameters and your zero shift. Zero shift is mainly due to instrument. Okay, and then also or your sample preparation, and then you are also taking care of UVW, which is again your instrument parameter. Okay, you are taking care of this in your profile fitting. So next, when you go for ritual fitting, you need to bring into or you should also take into account your intensity of the each peaks. Okay, so this is why I didn't prefer the poly fitting, because poly fitting can be sometimes it can give a lot of confusion. Okay, so uh, Libre fitting is really good because in that case you don't have to worry about the atom which is present. Then you can actually solve for your symmetry and also your ABC. Okay, and then if you want to solve for the real ritual refinement, then you bring in your the contribution of the intensity of your peaks. Okay, so then it will give uh, more information about the your atom which is present in your sample. Okay, so just to give this ritual method, the algorithm was developed by Hugo Rietveld. So this is he is the main person who is behind this algorithm, which will take into account all these intensities and all of this. Okay, so that is why it is named after him. It is called as ritual method or ritual refinement. So this is because it is from based on this or just to give credit for his contribution. Okay, so if you want to read more on this, there's a publication on Journal of Applied Crystallography. He did this in 1969. Previously, they used to use this algorithm manually by on a paper and using a paper pen. So it used to be very huge time taking, or it used to take a lot of time. So now you have a lot of softwares like your Foolproof, you have your EVA, Export High Score, Match, all those things. So these softwares normally use the same algorithm. Okay, so and then the only thing is the concept is same. Okay, whether you are using high score, whether you are using Jana, you are using GSAS, or you are using Foolproof. So this concept is same. Only thing is only some the graphics would change, the way you work on a high score is maybe easier compared to full proof, or the one the GUI that you use for GSAS maybe easier compared to Jana, something like that. Okay, it is just the program that it works. Okay, but anyhow, most of the concept is same. Whether you are using any program, they are using the same concept of Rietveld. Okay, so here, what are the things you need? You need to start with a really good crystal structure model. What is this good crystal structure model? That means you need to start with a good ABC parameter. You need to start with a good space group. Okay, and then you need to start with a good XYZ parameter. For XYZ is the atomic position parameter. Okay, so for example, if I have a simple cubic, which is your primitive cell. So if your sample is a primitive cell, and if I use Fm minus 3m, that means I'm starting with a wrong model, right? Because this is a face center cubic, but your sample is primitive, which is your simple cubic. So in that case, I have to use Fm or some Fm minus 3m or something like that. Okay, I cannot use Pm minus 3m. Okay, I cannot use Fm minus 3m because this corresponds to face center cubic, not a primitive cubic. Okay, so this is the meaning of good crystal, good starting crystal model. Okay, and then I cannot give my XYZ as 1 by 2, 1 by 4, and something like 1 by 3. Okay, so this is an arbitrary number. If I'm having a simple cubic, then it can be 0 0 0. So this is your 0 0 0. Then this is your, if I take this is my x-axis, then 1 0 0. And then if this is my y-axis, then it is 0 1 0. And the last one is 1 1 0. If I am taking two-dimensional one. Okay, so these are the atomic positions. So this is your x, y, and z. Instead of this, I cannot use some arbitrary number. So this becomes a wrong model. Okay, so this is the meaning of your good starting crystal model. Okay, so apart from your good data, you need to start with good model. Okay, so these things you need to take care when you start your Rietveld refinement. So then what is it good for? So you can do a crystal structure. You can derive a good crystal structure from Rietveld refinement. You can also derive a quantitative analysis, like if you have two phases, like we saw in the previous case, if I have CO2 and mixed with some SiO2 or TaO2, then if I want to know the distribution of this Rietveld refinement will help you. Okay, so to get the very to get the what is this distribution, phase distribution. Okay, if I am having 75% of CO2 and if I am having 25% of SiO2, then you can derive it from doing a really good Rietveld refinement. Okay, and you can also do some microstructural information. So this I will try to cover in the tomorrow session, because it will be difficult to cover everything, and also it will be sometimes it will be too much for in a one day. Okay, single day. So what we'll do is we'll try to do only simple example like your CO2 or TaO2, and then if we have time, we will try to do a mixed phase. Okay, so that is our today's plan. So let us see how it goes. Okay, so then next, some of you were asking what should be the RWP. So for this, you should know what is your RWP and what is your RP. Okay, so RP refers to your this is your residual. R refers to residual. This is your profile. P means profile. Okay, so how to know what is the residual profile? So this is the formula that is normally used. Okay, when you do a profile fit or a Rietveld fit, you get these RP, RWP values or EXP values in your out file, or even when you run in your full proof, it shows all these things. Okay, so you should know what is meaning of this. So residual profile means it is this is your formula. Okay, normally what you do is you take y means it is your intensity. Okay, the observed intensity minus your calculated intensity by your observed intensity. Okay, so this is your uh, this is sufficient for your profile matching or profile fitting. Okay, when you're doing only profile fitting, then you can use this. Okay, RWP. So this will give the goodness or how good is your fit. Okay, then when it comes to your weighted means it has some more contribution. This is similar to RP, but there is an extra term which is WI. Okay, so this is due to when you do your more quantitative analysis. Okay, then there is next term is your R experimental. R experimental has the term of n minus p and c, which is n is the number of points in the pattern. So that means if you take more number of data points, that is your n, and the number of refined parameters, and then your c is the constant. Okay, so these things are again taken care by your program. So at this stage, I don't want to confuse too much about this W and C, all those things. Only thing is, if you have more number of data points and if you are having, if you are refining less number of parameters, then you get a better fit. Okay. So, and then how to define a chi-square? Chi-square is nothing but RWP by RESP whole square. Okay, or chi is root of this. Okay, so this is the meaning of chi-square. Okay, when you do this chi-square, when you say chi-square, what is the meaning of chi-square? This is nothing but how good is your fit. Okay, so RWP divided by REXP. Then for crystallographic model, sometimes you can also have Bragg factor. Okay, so this is the formula. So I think if I keep talking, it will be just taking time. So instead of that, what I will do is I will just go to the next slide, and then I will summarize this talk. Okay, so when it comes to Rietveld refinement, so it is consisting of your crystal or magnetic model. So for example, if you're doing a neutron diffraction, then you can also give the magnetic spins, which is your magnetic structure. Okay, but in our case, we will be talking only about the crystal model. Okay, crystal structure. So we will give only the Rietveld refinement will in our case, we are going to do more crystal structure refinement. Okay, where you need to take care of the intensity in the sense the atom which is present in your sample, how many number of atom is present, what is the scattering factor of that, all those things we are going to take into account when you do the Rietveld refinement. Okay, so when it comes to Rietveld refinement, what are the things that you are going to change? So in case of your profile fitting, so if I put a profile fitting, what are the things we changed in your profile fitting is we changed your zero. Okay, zero parameter. So zero is it takes care of your shift, zero shift or your sample height. Then we also changed the ABC parameters, alpha, beta, gamma parameters. So this is about your crystal lattice. Okay, so this then we also changed about XYZ, XY, and then UVW. Okay, so this is these are things that we fitted. Okay, but when we come to the Rietveld refinement, yeah, in case of zero, we'll stop all these things. That means first we will do a profile fitting and we will fix all the values. Once we have good profile fitting, we fix all these values. Then what we'll do is we are going to change scale factor. We are going to change isotropic factor. We are going to change XYZ. That is your atomic positions of your atoms. We will also change the occupancy, and also we are going to change the D-iso. D-iso is nothing but your thermal parameter. Okay, so as I told, even at room temperature, which is your 300 Kelvin, your atoms will be having small vibrations. So this is taken care by your B-iso. Okay, in your model. So all these things we are going to change. So this is why I went step by step. Okay, so if I want to do Rietveld refinement, I cannot just directly do Rietveld refinement. Okay, I need to know what is the space group. I need to know what are the ABC parameters. So that is done by your phase identification. So we use this phase identification by doing your QLX. Okay, so from there I got what is my space group, whether it is I4 by I4 by AMD or something like that, or if it is a FM minus 3M or PNMA. Okay, all these things I get it from my phase identification. Okay, so if you don't know how to do phase identification, or if you don't know why you do phase identification, then there is no meaning in doing a Rietveld refinement. Okay, so this is one reason I started with phase identification. Then what we did profile matching. So profile matching will take care of your instrument contribution, like your 0, X, Y, U, W, and then it will also take care of your ABC and space group. Okay, so these information you get it from your profile fitting. Then what you do when you want to do a really good ritual fit, you need to bring into or you need to start putting the information about the type of atom. Okay, what is the atom which is present inside, and what is the position of this atom, and what is the occupancy, how much it is. Okay, so for example, if I take CO2, there is one cerium, two oxygen, and if I dope with something, then what happens in the place of cerium oxide, I may have some secondary element like your silicon. Okay, so I can have silicon in some place. Uh, uh, then what happens? I need to give this occupancy. Okay, and also iso this atomic temperature parameters. Like if it is at room temperature, then this cerium may be vibrating. If I increase the temperature, then what happens? The vibration of this cerium is going to will be increasing, right? So that has to be taken care by fitting in your fitting. So that is taken care by your BIs. Okay. So these are the things that you should know before doing your profile fitting, or sorry, your ritual fitting. So now, so all these things are linked. So you cannot directly go directly to your ritual refinement. You should start from phase analysis, then do the profile fitting, and then you can do a very good ritual refinement, okay, or meaningful ritual refinement. Okay, so then how to know whether it is a good fit or not? So someone was asking yesterday how to know if this is a really good fit or not. So this good fit depends on your all these factors. So as I explained in the previous slides, so it depends on chi-square. In some cases they call it as GOF. Okay, for example, if you're doing if you're using your JANA, or if you're using GSAS, so normally they call it as goodness of fit. Okay, so what is this goodness of fit is? Goodness of fit is nothing but is the chi-square. Okay, so your reduced chi-square is called as the goodness of fit. So I will give all this information, or even I will share all this PPT. So then you can keep this as a reference. Okay, so but do you say how do you say it is a very good fit, or how do you say, how do you tell the quality of the fit? Is it by having a small chi-square, or is it by having a small RWRP? But it depends on each sample. Okay, and also the instrument. If you are using an instrument which is not having good resolution, you cannot reduce your RP. If your RP is not reduced, then RWP is not reduced. If your RWP is not reduced, then your chi-square is not reduced. Right? So everything is linked. So there's a large, or even today there is a lot of debate on this kind of okay, telling whether it's a really good fit or not. So best thing is, so you just go with this. Okay, if you are having a good visualized fit, like if you have so this is my peak, and if I'm having a good fit of this peak, okay, so then I can say, so this is a good fit. Okay, so don't worry about chi-squares, RWP. It depends on a lot of factors, as we saw already. So it depends on your profile. So if your experimental data is not good, then you can never have very good RP. If you don't have very good RP, then your RWP will not be good. Okay, same thing with your REXP. And when you come to chi-square, chi-square depends on RWP and REXP. Okay, so that is the reason. Even if you go to some neutron diffraction data, and if you see the published data, so sometimes they give chi-square is almost 4 5. Okay, that is mainly because they might not have very sufficient time uh, to to get a good data. Okay, so because a neutron to get a neutron neutron beam is not easy, because there are very less neutron facilities. So in that case, what happens, they might have taken data only for some 1 hour 2 hour instead of 8 to 10 hours. So in that case, you cannot have a good profile. If there is no good profile, then your chi-square can never be small. Okay, so this is the reason you don't worry too much about chi-square, what is chi-square, what is GOF. So so even if you have sufficient good fit, when you see this fitting visualization, so that is what we did in the previous case. So what is the meaning of a good visualization means? You should have your OBS and minus y calculated should be very small. That means it should look like a very straight line. Okay, so then that means it's a good fit. Okay, so these things you need to take care, and then when you try to publish the data, you can give this RP, RWP, and then chi-square values. So that will give some information. But if they ask why is your chi-square not less, they will ask, okay, your chi-square should be close to 1, or they will say your chi-square should be less than 3. It depends like how good is your data. Okay, so sometimes even there will be a lot of scattering from your sample. Like if you're using highly fluorescent sample, then you'll have a lot of background, right? Lot of noise. So if you have this lot of noise, then your RP cannot be small. Okay, again, these are some of the reasons why you will not get the chi-square less than some value. Okay, and if there is a lot of anisotropy in your sample, again your chi-square cannot come down. Okay, so that those are the things why you have a high value of chi-square. So this comes with experience. Like as you keep doing more number of Rietveld refinement, you will know what are the different contributions for this RP, RWP, chi-square, all those things. Okay, so for right now, I think we will stop at this point, and if you have any question, I will take the questions. So this we will I will explain you. Okay, so when it comes to bar, you need to have you have to just put minus. Okay, so if it is something like this, fm 3 bar m, then what happens when you write in full proof, it will be m minus 3 m. Okay, so instead of bar, we are going to use this minus. Okay, so this is how we are going to do. So we will take some examples and we will do it, okay, in the next session. So if you don't have any other if you don't have questions, we'll take a break for 30 minutes. So we will start again at 11:30. Okay.